a pretty comfy seat here. Nice little bathtub. Because what do you fill up with bathtub? Not Jello, but water. And we're going to be talking all about water today, including the properties of water. So water has a lot of really amazing properties that make it what it is. We cannot live without water. And water can't help us unless it has these really unique properties that not all liquids have. So I have a series of different types of experiments that we can look at these properties up close and talk about how they impact our life every single day. But first, a little bit about water molecules. So we've all heard of H2O. And what that means is that there are two hydrogens and one oxygen. So H2O. Now, what's really cool about these molecules is they have a positive end and a negative end. So that means, like a battery, here you have your negative end and your positive end, that electrical current can go through and connect to other things. The same thing happens with molecules. So when you have a positive end and a negative end, those molecules will stick together. And that sticking together is what's really, really, really cool about water, because we get two different types of things. We get adhesion and cohesion. So over here, adhesion is that water molecule will stick to other things. Pretty important. Cohesion is that the two water molecules will always stick together. So water likes to stay together like the buddy system, and with that can produce a lot of other different qualities of water. So let's look at those a little bit closer up. With adhesion, I can take water and put it on a surface, like so. We're going to use the penny. And it's going to stick to the penny. Now, if I put another drop, it'll stick to the water, cohesion, as well as sticking to the penny still, adhesion. So I'm going to see how many drops of water I can get to go on this penny. And this is something you could even do at home. You don't need a pipette or anything like that. You could just use a paintbrush or a toothpick to put those drops of water on the penny. Oh man, I wonder if I can fill this whole penny. Oh, couple more. Whoa, can you see how that's bubbling over? So that's that cohesion, sticking that water together, making sure it's staying really close, tight knit, and it's sticking to that penny with the adhesion. I don't know how many more I can do. I'm gonna get some more water. This is amazing. Oh, there it goes. Pretty impressive. We can also see this by stretching the water. So I can put it on here. You can do this at home with just a ruler and a table. I have this nice little page that allows me to do it. So I'll put some water on, oops, my paper. It's already starting to move away from me. So that adhesion means that it's sticking close to here. The cohesion is staying together. And I can take this toothpick and I can stretch it super far. So I don't know if you can see, it went from just 1 centimeter to almost 3 centimeters now. Right? 1, 2, almost 3. So you can stretch that water and it's going to want to stay together. Now, oftentimes we can see this every single day with adhesion, raindrops, like today. Today in Duluth is pretty foggy. There was a little bit of rain this morning, at least at my house. And you can see the raindrops attached to the window and slowly roll down. So that's that adhesion, staying onto something else. Now, when we put these together, we also can see surface tension. So surface tension is when the water molecules all are sticking together, they're hanging on tight and they're going to resist something breaking through their kind of wall of molecules. So to show that, we have this neat experiment. I have my bowl of water, and if you just take a paper clip and drop it in pretty fast, it sinks right to the bottom. That's because there was enough force to break through that surface tension. But if we take another paper clip, so it's the same type of paper clip, we can try to make it float. Now, I'm not going to guarantee that I can do this on the first try. It takes a lot of patience and a steady hand. So I'm going to try to do it. I'm going to try to put it in the water, nice and slow, as to not disturb that surface tension. Oh, I almost had it. Let's try again. It hit my fork. All right. Woo. Sticking to my fork. There we go. So now the paper clip is floating on the water because of that surface area or surface tension. So those molecules are resisting the weight from the paper clip going down. We can see this a lot with different types of water insects, like water striders. They have those legs out on the water and they're utilizing that surface tension to stay up on top of the water instead of floating or sinking down into it. Pretty impressive. Again, these are all things you can go do at home. I actually put a link in the description here that has step-by-step instructions on how to do some of these experiments. Now, if we continue to put all of these things together, all of these amazing properties, we can see water do some really cool things separate of just those. Now, important in plant life is capillary action. So that's the movement of water through cohesion, adhesion, and surface tension. So we're putting all of these pieces together. And that's like if you were to take a napkin or a piece of paper, a paper towel, with some water and put it into the water, we can see that the water is moving up the napkin. That's that capillary action. So water is going to keep on moving up as long as gravity allows it. So it's going to stop eventually because gravity is going to have too much force keeping it from moving upwards. But until that happens, it's going to keep on climbing and keep on climbing. This is important in plants. If you think about them taking water out of the ground, up their root system, this is how it's happening, using these three properties. Pretty cool. We can also see this in water moving in more ways than just up. So I have a piece of string here. I let it soak in my water just for a little bit. I don't want it super, super wet, so I'm taking some of the water out. And I'm going to put it in a cup half full of water. If I put my string over here, I'm just going to hang on to it. It's just hanging above the other cup. Place my finger on this side of the string, have it straight. We're going to see that cohesion come into play. So the adhesion is that it's sticking to the string, but eventually, as I start pouring the water, you would think I would make a mess. But due to cohesion, it's going to run down the string, staying together. I'll let the camera come up really close. So that's that cohesion. So cool. I could watch this for hours. Now if I put too much force, it's going to spill a little bit, but for the most part, it's going to try to stay together. So you can see there. Gosh, water is just so cool and important. So all of those help in a lot of different ways. We've talked about plants getting water. We've talked about animals being able to maneuver around water. But water has even more amazing properties. Besides being a great solvent, so if you've ever put salt into water, it dissolves. That means water is a solvent. Things can go into the water. Sugar, salt, all of that stuff. It's also polarized, so when we talk about how there's a positive end and a negative end going together, density, all of these really great properties. But my favorite is a high heat capacity. So if we look over on our board, that means that water has the ability to absorb a lot of heat. Now we talked a little bit about this last week when we talked about climate change, because this is where it really comes into play. Big bodies of water and small bodies of water takes a lot of heat for it to soak on up. And it also means a lot for that heat to be released. So having a high heat capacity is pretty important with water. It can do things like help us in industries. So as a coolant, if something's really, really hot, we can put water on it to cool it down because it absorbs that heat really well, like a car radiator. But on a grander scale, it also impacts our seasons and our climates. If we didn't have high heat capacity in water, our seasons would change way too quick. So instead of having spring and fall that are gradual, instead that water is absorbing heat and slowly releasing it, allowing for those seasons to have that nice change all the time. So it's pretty important. To show you high heat capacity, I have two water balloons. One of them is just full of air, just like so. The other is full of water. Now, I have a heat source, I have a lighter, and as a scientist, you should always make a hypothesis. So, I hypothesize that if I heat up this balloon, the air is going to heat up really fast, and I might get startled. Now, we test our hypothesis. Heat. Whoa, that was really loud. So, the balloon popped. Our hypothesis was correct. So now, we have one full of water. And remember, water has a high heat capacity. So, oh boy, I really don't want this to pop on me. I can heat this up. My hypothesis, I'm going to go the opposite of that one. Partially because I've done this experiment before. But I am still going to make a hypothesis. I hypothesize that if I have a heat source and I put it onto the balloon, the high heat capacity will absorb enough heat that this hopefully will not pop on me. No change. High heat capacity. So important with water and pretty unique. Not all liquids have such a high heat capacity. So something might boil faster than water. That's because that heat capacity can vary based on different liquids. And that could be because there's a different mineral in it, there could be different types of chemicals moving around. But water, a constant in our life, has that high heat capacity. Super important. Should we see how long it takes to pop? I'm kind of curious now. Abby, who's behind the camera, if we had to hypothesize, how long do you think I can hold the flame to the balloon until it pops?
I'm gonna go with a solid guess of 2 minutes.
2 minutes?
I think you could talk about water and we'll just see how long it takes of you talking about water before it heats up.
Okay.
I can set a little timer.
So we are going to hypothesize.
For science.
For science. This is live science right here. We don't know the answer to this.
All right.
So the hypothesis is that it will take 2 minutes for this water balloon to pop based on the heat capacity. All right, timer ready?
Timer's ready.
Let's go. Oh, I'm so nervous. I wonder how long the plastic will hold before
I think the plastic would heat up before the water. Or all the water anyway.
I'm so scared. Oh God. It's like kid watching this, make sure you have a parent supervising and helping you, and never do this on your own. Always have parental guidance. I am going to be 28, so I feel like I can give myself parental guidance doing this experiment. I also have Abby here helping me, so safety in numbers.
We're at about a minute.
Oh my gosh. This is taking so long. Wow, this is so amazing.
Now that water is keeping it together, staying cool.
Oh no! There we go. I don't know if it's like gonna break.
Maybe it won't. Never know.
What's our timer at?
It is at 1 minute, 40 seconds.
Oh,
We're about to
I don't know.
about to ruin my hypothesis here.
I saw a water bubble.
Oh, you're seeing water on there. You can kind of see it a little bit.
Should have gotten a candle.
Yes, that would have been easier.
I think we passed 2 minutes.
Yep, we did. We're at 2 minutes, 11 seconds.
So we're starting to see some water in there. So I'll give you a look.
Having trouble focusing on that. There we go, a little bit.
Wow, and the water balloon is starting to feel pretty warm. Warmer than it was. Can you feel that, Abby?
Yeah, it's a little warmer.
Yeah, but it's not hot.
Mm-mm.
You'd think it'd be hotter with flame going on it for like 2 minutes.
Imagine trying to boil pasta with a lighter.
That would take
Yeah.
a long time.
A long time. We're very lucky we have stovetops.
Yeah. And if you've ever heard the phrase salt your pasta water, that salt helps change that heat capacity so that your water boils faster and adds flavor to your pasta.
Which kind of explains the oceans, right?
Yeah. Can change that
Warming
heat
up a little
capacity.
faster. Mm-hmm.
Oceans warming up, like we talked about on last Friday. I don't think this is gonna
That balloon
pop.
is scaring me.
Yeah.
We're at 3 minutes, 21 seconds.
Oh, jeepers. You feel it.
It's warming up a little bit, yep.
There's a little bit of water, so showing that adhesion.
Or is that
cohesion.
plastic?
No,
No, that's
it's
water. Okay,
yeah.
okay, that's water.
It's water coming through. Again, remember parental guidance and permission to do this experiment. I'm sure my parents are watching this video, and
They
if
are.
they knew I was doing this, they would give me permission, I hope.
For science.
For science, of course. Alright, I think we
There we
almost
go.
have to call it. Like, I don't know how much longer my finger can stay.
We're past 4 minutes.
So more than 4 minutes, we're holding heat to this balloon. And it's still sturdy. But it is getting kind of hot on the side. Can you feel that, Abby?
Oh yeah. Yep, it's getting warm.
Amazing. So cool. And it just was like milliseconds for the air one to pop. So that shows that high heat capacity. So, those are all just things you can do at home. And water, like I said, has some amazing properties. But it's not just cool because of its properties, it's also because it's essential to our lives. We use water in every part of our lives. From making materials that we use, drinking, staying healthy and hydrated. It helps grow our food. Every part of our life, water has some sort of hand in. So it's super important to make sure that we're doing what we can to protect the water we have. On our planet, a huge chunk of the Earth is water. It takes up about 90% of the Earth's biome, so that livable space that we're on our planet. So if that's that much water, and 97% of it is in the oceans, that's salt water, think that even says it right up here.
Sure does.
97% of the Earth's water is salty. That means we can't use it. And then if we go by, the 3% that is fresh water is divided between glacial ice, groundwater, atmospheric vapor, and surface water, so lakes, rivers, and wetlands. The water we can actually use is that groundwater and surface water. That's not a lot in compared to the world's water. So we should be doing everything we can to protect it so that way we can still live. Everything else around us still can live. And we can stay healthy and happy here on our planet. So, my goal for you all is to think about ways that you can protect your local waterways. So whether that's using less pesticides that could get into our water on your yard, or going around and cleaning up trash around lakes and rivers and streams, or even just talking to your friends about ways that you can get together in your community to promote healthy water. Super, super important. And if we all do a little bit and we all work together in our communities, that can spread to a state level, to a national level, to a worldwide level of making sure we're doing what we can for water. So with that, I hope you join us tomorrow where we take all of these amazing properties and we start looking at how animals here at the aquarium use that water, both for swimming and floating, staying buoyant, all that stuff. We'll talk all about that tomorrow's video, live at 1 p.m. And with that, thanks again for all the support we see from the community and those who are watching these videos and everything. We seriously, seriously, seriously appreciate it and cannot do what we do here at Great Lakes Aquarium without all of you. So thank you, and I'll see you tomorrow.